Having introduced Stokes' theorem in the last video, this video will constitute an example where we'll evaluate both sides of Stokes' theorem to show its validity and to show that one of the sides of Stokes' theorem will be easier to calculate than the other. So in this example, we want to evaluate both sides of Stokes' theorem for this particular vector field over the semisphere and the upper half of the z-plane, so when z is positive, of radius a. So it looks something like this. It's just half of a sphere above in the positive z-plane. There's a number of ways that we can do this. We can immediately translate all of these to spherical coordinates, but we'll see that when we calculate the curl, a lot of things will simplify and we don't actually need to transform this vector field into spherical coordinates. However, because we're going to need to evaluate a surface integral, we are going to do it in spherical coordinates. And because we're dealing with a sphere, we know that the surface element is equal to the radius of our sphere squared, so in this case a squared, times the sine of the azimuthal angle. And because we're going over the surface of the sphere, the radius doesn't vary, so there's no dr, but we're varying our azimuthal angle from the top to halfway to the other side, and our polar angle across the entire xy plane. And the normal vector to our surface, because it's a sphere, is the radial unit vector, r hat. So we can begin by calculating the curl of this vector field. And we'll stick to Cartesian coordinates just because it will quickly simplify. Remember, when you calculate the cross product, one way of doing it is to calculate the determinant of this matrix. So you have the components of the gradient and the components of your vector field. And you should try to do it yourself. What you'll get is 0 in the I hat direction, 0 in the j hat direction, and a -2 in the k hat direction. So our surface integral, curl of phi times our surface element, which we know should be equal to this. We calculated the curl, which was -2 k hat. The normal to our surface, because it's a sphere, is in the r hat direction. And our area element is given by a squared sine theta d theta d phi. For the limits of integration, our azimuthal angle, remember, goes from positive z all the way to negative z. In this case, because we're only looking at half of the sphere, it'll only go from 0 to half of its range, so pi over 2. Our polar angle goes from 0, and it has to go all around the entire base of the sphere. So it goes over its entire range, 0 to 2 pi. So this is then equal to -2 . d phi 0 to 2 pi, 2 pi over 2. Okay, so we can split up our integral like this. This component we'll see depends on theta, so that's why we're leaving it in this integral, and this is completely independent from the other one. Now the dot product of k hat with r hat, you have to remember that k hat goes only along this direction. So by definition of the azimuthal angle, the angle that set makes with the radial vector is just cosine theta, and they're of unit length. So k hat dotted with r hat is just equal to cos theta. And we'll skip, we'll do an extra step here. We'll immediately evaluate this integral because it just gives us the difference of the boundaries. This will be minus 4 pi. It should be an a squared from over here. A squared. This is from the dot product k hat dot r hat. And cosine theta times sine theta d theta. And you can evaluate this just by regular u substitution, and you should get minus 2 pi a squared. Okay, and I encourage you to go through the details yourself and make sure that you understand this. Okay, so for this video, we'll just do the surface integral. In the next video, I'll show you how to evaluate the other side of Stokes' theorem, which involves a closed loop line integral over the path that encloses this surface.